to learn something, like our brain systems. Yeah. And then maybe assign most difficult job to the robot to predict or understand the materials better than humans. The issue I brought up this kind of thing is that even though we have a very good robot, also very good softwares, the most important issue is that can we establish database, material database, like thermodynamic database, or electrochemical database, or material properties, or mechanical properties, or optical properties, or magnetic properties. That's all the material properties. But machine learning is nothing but once we have the database, we can assign the robot to learn something. But if the database, the data sampling is not accurate, robot just give us garbage. Computer doesn't do anything. If you put garbage, you can get garbage. But if you provide a very good, accurate database, they do very good job. That's, clear. Yeah. So I'm going to show that how to we establish the database for material properties. Yeah. Here, thermodynamic, kinetics, electrochemical, and optical properties. Can you establish this database? Then you can assign this database to the robotics to learn, the database. Let me show something. Example we have done for last 2 years or 3 years in these sectors. I'm going to show you that first principle calculation can predict the material morphology. Let me show the material morphology under vacuum conditions. We predicted aluminum nitrate powder. This is a very important material in the display materials. This is actually chosen at cover of the journals. We predicted the material aluminum nitride topology by using first principle calculations, and actually they synthesized exactly as the computational predictions. We also designed that multi-component systems. For example, the target was that can we design kappa very strong, also very conductive. There is a huge, very strong conventional law that if you want to increase kappa electric conductivity, you have to lose your mechanical properties. That's actually governing law by conventional theory. But then we need a very good, careful design from atomistic levels. Otherwise, we cannot get over these conventional laws, limitations. So we designed kappa matrix, and we dispersed gamma alumina nanoparticles, and also we dissolved trace amount of titanium. Then what happened is that without titaniums, we figured out that gamma alumina oxide looks like that. Very fuzzy type of topology, as experimentally observed. This is computational predictions. But if you assign a little amount of titanium, the topology completely change in the shape spherical types. In the mechanical engineering, once the dispersed particle has spherical types, then it is very good for mechanical strengths. Also, this spherical type does not block electronic scattering, electronic propagations, which means that electric conductivity is not degraded significantly. So we achieved that by combining experimental measurement and the computational predictions. We got the best performance in the world. This performance have never been achieved before. So this is kind of good example how the computational prediction and the experimental validation can achieve good performances. How about alloys? Typical alloys in the nanoparticle sectors. We can screen out here. We have thousands of material candidates. You can quickly calculate if you got assigned. Can you predict platinum, let's say platinum, nickel, or cobalt, the most stable structure? Of course, you can do by computational screening. We have thousands of typical candidates, and you can sort out the most stable configurations as function of alloy compositions very easily, very quickly. And you can provide this database of information to experimentalists. Can you design this material? Of course. Some experimentalists want to design, for example, these materials. Certain compositions you cannot design because this is not stable. Yeah, just forget about it. Then experimentalists, they can save their money and time. How about graphene? Everybody talking about graphene nowadays. Yeah, graphene is not itself is not good, but there is like some behavior to adopt some heterogeneous atoms on the graphene. For example, many people is working on the graphenes. This is a single layer of carbons, And can you dove nitrogen on the graphene? Of course you can do, but you cannot more than 30%. This is maximum concentration of doping concentration by nitrogen on the graphene. If somebody just reported that, oh, we synthesize more than 30% nitrogen on the graphene, no, it's a fake. Because more than 30% of doping give you two-phase regions. It is not really graphenes doped by nitrogen, but it is nitride, not graphene. Okay, so that's kind of also things. I'm going to show the second example is that, can you predict the structure on the aqueous solutions? If you put nanoparticle on the aqueous solution, can you predict the structure? Of course, you can do. We can screen out most of the different topologies, and we can screen out the most stable structure as a function of oxygen partial pressure. Here, this picture shows that platinums, very low oxygen concentrations. You can have a very nanoparticle cell. But if you increase oxygen partial pressures, platinum does not oxidize. That's why you are using platinum as a wedding ring. But in nanoparticle, platinum do oxidize. Yeah, don't give nanoparticle platinum to your wife. They'll be oxidized like that. And even oxygen can propagate or diffuse into the surface base of platinum nanoparticles. Platinum complete buttons, decayed, and then you are losing the all properties of platinum. This figure shows that this was done. The first in the world. Also, you can predict experimental measurement. How many people you understand the cyclovoltammogram here? If you increase chemical potential, electron potentials, you're gonna see this peak. You can measure the experiment peak in the experiment, and you can predict any peak. What is the structure of the platinum nanoparticle in aqueous solutions? Yeah. If you give this map to experiment peoples, they can validate our result accurately. Yeah, like that. The other topic is that how platinum is unstable in the nanoparticle regime and the aqueous solutions. This is we know that this is Pouvet diagrams. Belgium guys, he spent all his life to measure the stability of any material in the periodic tables. The missing information is that there is no Pouvet diagram in nanoparticles. Yeah. No information in nanoparticle Pouvet diagram. So we try to predict electrochemical stability of platinum in aqueous solutions. This picture shows that the Pouvet diagram, the first in the world. When I was in MIT, I did this one. This picture shows that platinum nanoparticles dissolve 0.7 volt. In the meantime, platinum, the bulk size of platinums, the wedding ring, right? They dissolve only like in these axis solutions. They only dissolve at 1 volt above, with respect to standard hydrogen electrode. But nanoparticle of this size start to dissolve at 0.7 volt, which means there are huge decreases in the electrochemical stability, right? You know that electrical vehicle driven by hydrogens, they are utilizing platinum as a catalyst materials. But pure cells, mostly the potential window and the pH windows like that, very strong axis solutions and above 1 volt, which means platinum nanoparticle of this size should not be utilized as catalyst materials. Otherwise, we need a better materials than platinums. Also, this result was validated by in situ STM in another group, not in MIT. The other groups, they measured the dissolution potential as a function of particle size. They scattered platinum nanoparticle as a function of different size on the gold support, and they kept certain potentials, maybe 10 minutes or 20 minutes, and then they figured out certain material is gone here. 4 and 5 is gone. They know exactly the size of 4 and 5. Okay, number 5 nanoparticles, they dissolve at 0.6 volt. So they kept the record by hand. Then they compared our result, and then we figured out very good agreement between experimental validation and computational predictions. Okay, so one or 2 nanometer platinum particle dissolve less than 1 volt. How big the particle should be to keep above 1 volt of dissolution potentials? Because people want to know. Company Ford or Hyundai, Honda, Toyota, they want to know how big platinum particle they have to use to keep the dissolution potential above 1 volt. Our computationals shows that even 3 nanometer is not enough to keep the 1 volt of electrochemical stability. We need much bigger than 3 nanometers, which means you are losing the benefit of platinum nanoparticles, right? The only benefit of nanoparticles is that you have much wider surface area compared to bulk. So if you're using very huge nanoparticles, you're using the benefit of platinum nanoparticles. But anyway, this is unfortunate, but I mean, single pure platinum nanoparticles, I mean, it's not good catalyst material for hydrogen-driven electric vehicles. Now, these days I'm working on the different media. For example, the lithium manganese oxide. This is an important cathode material of lithium-ion batteries. And what happens if this electro oxide material exposed to carbonate electrolyte? There is a oxidation, reduction, redox reactions between the cathode material and electrolyte. Electrolyte decayed out by certain reaction with the electrode, and there is a instability issues in lithium-ion batteries. This was also chosen cover of the journals. How about molten salt? Molten salt which means liquid solutions but high temperature, right? So you're gonna see two different pictures. I used this project for how to recycle nuclear waste from the nuclear power plants. You know that in South Korea, we are abolishing nuclear power plants by replacing the energy by renewable energy. But I don't believe renewable energy can replace whole nuclear power plant energy. That's absurd, stupid project, I think. But nuclear power plant in Korea support more than 35% of electricity. I don't think renewable energy can provide that much energy anyway. But anyway, 1 year or 3 year or 5 year, depending on nuclear reactor types, once you burn out uraniums in nuclear power plants, there is still many of uranium is not reacted. So we want to recycle nuclear fuels from that spent nuclear fuels. Once you take out spent nuclear fuel and you dissolve in molten salt, and you want to recycle exactly uranium, not other materials. There are huge amount of uranium or huge amount of rare earth materials. Most of rare earth reservoir in China now. Right? So we're going to take out separate uraniums from rare earth materials. So we need a very good electrode materials to only selectively take out uraniums. We are currently developing tungsten electrode in molten salt, basically a chloride molten salt, NiCl, KCl molten salt. You're going to see that two different pictures here. The first one is that tungsten electrode and uranium nanoparticles, how they do form the morphology. They do form flat type, monolayer, layer by layer structure. How about in the vacuum conditions? How about in the molten salt conditions? You see that the topology is very different. Uranium in molten salt, green is actually chloride. Uranium grow in the dendrite formation, dendrite form, not the flat type. So many people predict using computations the topology or nucleation or growth behavior in vacuum conditions. That should be wrong. You have to incorporate the effect of chloride here, molten salt effect. The topology is very different. What about experimental measurement? Experimentally, uranium grow in the dendrite topology, not flat type. So this picture again shows that correctly simulate the medium is very important to prediction of material growth. Yeah, I told you that we have huge amount of spent nuclear fuels discharge. In worldly, here globally, every year we are producing 10,000 metric tons of spent nuclear fuel. In Korea, about around 900 metric tons of spent nuclear fuel every year. So this is a serious problem because USA does not allow Korea to reprocess spent nuclear fuels. We have to store all this material inside of nuclear power plant. We cannot take out any single metric ton of uranium. So, now Korea, the nuclear power plant are saturated with the storage capacity of spent nuclear fuels. Already one plant has reached that one. So our government shut down the nuclear power plant, one of the nuclear power plant in Korea. So we need better solutions to solve these issues, right? One of the issues that, as I told you here, the type processing. We just selectively recycle spent nuclear fuels. Then you can save the amount of actually the waste, nuclear waste. This is typically designed pyro processings. Yeah, they're using high temperatures pyro, and they are using molten salt to selectively take out uranium or platinum. Okay, yeah. Another issue is that this is another cover journals, top journal in nuclear engineering. We are going to selectively attain also rare earth materials. Typical archetype example of rare earth is that europium. Europium is very important material actually in the display. Your cell phones, all of cell phone has europiums. So we Korea doesn't have any reservoir of europiums. But europium in spent nuclear fuel dissolved in the molten salt a huge amount of rare earth materials. So we need a very good methodology to take out europium selectively. So we discovered the methodology, and we published paper in the certain journals. Okay. How about free energy? You studied in the high school or in undergraduate schools. What is the free energy means? Free energy means that characterize the spontaneity of the reaction, any chemical reactions, from the reactant to product. So once you know the free energy diagrams, you can judge if the reaction is allowed it, and if it's allowed it, is it spontaneous or non-spontaneous. So calculation of free energy is very important in chemical reactions. We could do that even as function of electrical potential, right? Electrical potential change the free energy diagram in the chemical reactions. This picture shows that the production of H2O from reaction of O2 and the hydrogens, is that reaction is spontaneous or non-spontaneous? You know that chemically they should be spontaneous, but in practice they never. Even though you put the oxygen hydrogen in this room, they don't react. Thermodynamically they should react. They should react, but actually not. So which means we need a catalyst materials. In platinum catalyst actually facilitate the reaction of H2 and O2 to form water. But the reactions, the activity of platinum nanoparticle catalyst material actually depend on the electrode potential. Also the facet here. This picture shows that typical nanoparticle has two different facets, one on surface and one zero surface, and there's empty side between them. This picture shows that platinum one on surface, this triangular type facet, is much better than 100. Yeah. What is important is that I can tell the experimenters that you need to save money, material money, because platinum is very expensive. Only South Africa, Russia is a reservoir. So you need only 111 surface. You don't need 100 because 100 is very bad in the spontaneity of the reactions. Just use a single crystal, no polycrystals. Okay, that's the first principle calculation message we can give to experimentalists. Okay, how about activity? Free energy only map out thermodynamic point of view. How about the kinetics? How about the reaction rate? You have to calculate activation barrier. Yeah. We can calculate using certain theories, transition state theory. Here the reason is that I applied this methodology to hazardous materials, because I was very surprised that government asked me to develop database for hazardous materials. There are many kind of different hazardous material. Even in South Korea, we have 69 hazardous material. For example, HCl, H2SO4, POCl3, PCl3. They are all cancer materials. Benzene, toluene, also. But I was very surprised. Honestly, I was so surprised because when I see the government database, they don't have a database. Unbelievably bad. That's why every risk is dumped to firefighters. They don't know how to extinguish the hazardous materials, how to nullify the toxicity of hazardous materials. They have to do by themselves, but they will die. Because our government cannot give you a database, cannot give the database to firefighters. Once they detected, there is some emission of certain toxic chemicals, but they cannot provide which material we have to utilize to extinguish the toxicity. So our mission is that can we make a database of any chemicals, hazardous chemical, 69 chemicals? Can you give us the enthalpy informations, reaction heat, or how fast they react? How they react in a humid environment? How do they react if there are other kind of hazardous materials? So we're gonna establish a database. Yeah. Okay, we did that. We could calculate activation barriers of different chemicals, then which means we can predict weight constant, how fast they react. So you need to activate your motion as soon as possible, because they are going to react in this time regimes. Okay. Also, we are developing something materials, metal organic framework, to protect soldiers or firefighters against the hazard materials. You can wear, this kind of mask, then you can survive for 1 hour or 2 hours, sometimes maybe 3 hours in the hazard material environment. Okay. Also, we are trying to develop other materials by using silver, and iodine gas is most dangerous materials. They have a long half-life materials whenever there is nuclear accident. So we need a very good materials protect against the iodine gas. I'm going to give you one example. You already studied that. I already mentioned that oxygen reactions can we reduce oxygen gas phase to O2 minus. This is one of the key reactions in many applications. I'm going to show the strong competition between Korea and Japan. We are going to develop hydrogen-driven car. Hyundai demonstrated in 2013 April in Denmark. They demonstrated SUV type hydrogen-driven driving car. But exactly 1 year later, 2014 April, Toyota developed Mirai, another hydrogen-driven car, and then now Honda actually involved in that competitions. So very strong competitions, but still Hyundai believe in that SUV type is better for future. But Japan think the sedan type is better. Hyundai is thinking of the only benefit of hydrogen-driven car compared to lithium battery is long distance driving range. Right? But Honda believe in that they want to commercialize even sedan type. They want to compete the lithium battery type car. But I'm working in the Hyundai, so I am pro for Hyundai. They give me another project. All right, but the problem is that the car price, you see here, just one car is about $85,000. Only maybe chairman can buy it. We cannot buy it. So the huge expensive material cost comes from here. Last year, I think I was in London. I was very lucky that I got lost in the city tours, and certainly some buses came up. I just get on the bus. I didn't know what type of bus is that, but I figured out later that the bus is hydrogen-driven bus. London has only 5 buses, so one of them I just get on. I was very lucky. London also tried to develop the bus type driven by hydrogens. Yeah, but anyway, this is huge. I heard that about $300,000 now. Very expensive. The problem of the material cost comes from the platinums. Yeah, I told you that oxygen, hydrogen react to produce water. Eventually, then you're gonna have a small amount of voltage. Yeah, this reaction should be thermodynamically spontaneous, but in practice, never. So we need a very good catalyst material to reduce activation barrier. So far, what we found is that platinum is the best materials. Only this size regimes. Yeah. Materials. If you find out better than platinum particle, I'm definitely sure you can get Nobel Prize. So this size only platinums. If platinum is very expensive, I told you that in South Africa, Russia, they have more than 75% of reservoir in the world. Korea no, China no, Japan no. So this is another issue of the oils. Yeah. So people in the advanced country, USA, in Korea, and Japan, they are strongly developed some other materials, alternative material to platinums. But unfortunately, the cost now it's 2010. Now 2018, the cost is by platinum is more than 50%, much more than 50%. So we need a better material, definitely. So far, we found out that platinum is best material, but still the activity goes on very quickly when you push the gas. If you want to go faster, the activity goes on very quickly. So it is a problem again. Also, I told you that electrochemical stability issues in excess solutions, platinum of this size regimes, they dissolve, very low potential, so they disappear just. Yeah, this kind of problems. So cost issues and activity and stability issues, the most challenging issues now we are facing it. Many people try to develop graphene types. Graphene got Nobel Prize. I invited Andre Geim, who developed graphene, right? Coincidentally, they use 3M tape. You know that? And they just put the 3M tape on the graphite and take off. And they found out one layer of carbon type was filled up, exploited. So they got Nobel Prize. But they didn't expect that much. You have to use only 3M tape, not other kind of company tape. 3M tape is only working. Very strange. Okay, but we found out that nitrile-doped graphenes, of course, they are good. The activity is almost same as graphene, as platinum. The problem is that if you design graphenes, the edge, there are always edges like that. Single layer carbons, they are already edgy, but this edge is not good because this edge is always poisoned by many different chemicals, hydroxyl groups, and different type of materials. Once they are poisoned by this kind of chemicals, the framework easily destroyed. It's kind of not stable. So even though graphene got conferred Nobel Prize, that material is not good for catalysts, for oxygen reactions. How about graphene overlaid by copper? They are good, but copper is not good whenever there is water. They easily oxidized. Yeah. So we tried many times. But how about graphenes using the blankets to enhance the dissolution potential of platinums? Yeah. Maybe if you carve a platinum nanoparticle like that, maybe then just trap platinum from the dissolutions. But what he found was that the dissolution potential enhancement is 15 millivolt. So forget about graphenes. Okay. How about I'm going to show this one is very important, I think. This is kind of inside the box. This data, this kind of methodology was proposed by Norskov, is Stanford University professors. Now he moved to Denmark. He was Nobel Prize candidate last year. What is the importance of his work? His work is goes like that. Okay, there is a catalyst activities. So I mean, from the experimental measurement, there are many different materials experimentally measured activities. Can we find out very strong candidate descriptors which can describe these material activities? Well, he found out that experimentally you can measure oxygen absorption energy on these different materials. Then let me give you the activity predictions. This is volcano curve, right? So many people try to design different materials which is like volcanoes in the located volcano. Believe it or not, those all materials are published in Nature and Science. Nature and Science. All of these materials published in Nature and Science. The problem is that nothing was commercialized. Nothing was commercialized. Failed. Completely failed. That's why he didn't get Nobel Prize. You can see that these materials, maybe if you read the papers, you see that how this theory is important. Provided insight how to develop further materials, how to develop new materials by utilizing only one single descriptors, but was not commercialized. This is me, sorry. This is Norskov. The issue is that there is strong segregation issues. For example, platinum, nickel, platinum, cobalt, each was provided by Norskov. They are very good actually. The activity is very good. The problem is that segregation of core material into surface. You see here, these materials all utilizing 3D transition method, nickel, cobalt, Fa, and cobalt, nickel, cobalt, iron, and nickel again. These materials very easily oxidize whenever there is oxygen. So Norskov proposed that you have to put this cobalt, iron, nickel in the core and coat the particle with a thin layer of platinums. Then you're going to have the best activity. The problem is that once you synthesize these materials and if you put this material in the oxidation environment, all core metal come up to surface if there is oxygen absorptions. To reduce oxygen, you need absorption of oxygens. That's inevitable. But then core material came up to surface. That completely killed your materials, right? Activity is not issues, but So they just killed catalyst materials, right? So we try to develop a better material. Binary compound is not good. Maybe ternary will solve the solution. Will solve the problems. So by collaborating with the Tokyo Institute of Technology in Japan, we try to find out better ternary compound. What we found is that copper and nickel and coated by platinum. As far as we know, this is best materials so far. I'm going to propose to synthesize this one if there is any experimentalist. The durability is good, activity also very much better than platinums. You need a half size of the platinum to keep the same stability. Okay? But eventually, I'm going to provide the new design concept here. As I told you, there's a very strong surface segregation of core metal to surface, right? Then dissolution issues. How can we provide the block surface segregation and dissolution problems? I'm propose that you can encapsulate the catalyst material by using carbon shells. Then these carbon shells regulate the oxygen absorptions and also block the dissolution of core metals. Right? It's working. We call encapsulations, and experimentally they designed experimentally. Here, copper core metal, and they encapsulate copper with a very thin layer of nitrogen doped carbon shell. Yeah, computationally, you need less than 1 nanometer thickness. 1 nanometer thickness is impossible, almost impossible, right? So how to control the thickness? So we provided methodology. If you utilize nitrogen fragment by doped nitrogens, you can see this kind of self-assembly type. Yeah, okay. Nitrogen doped carbon fragment, graphene fragment, we found that there is self-assembly. So if you put nanoparticles on that center, probably they wrap up nanoparticles by sample assembly type. So it's Chinese or Japanese sushi type. So you don't need to worry about the control of the thickness. It was published in a cover page of Nanoscale journal. Okay, I think you pretty much bored it now. I'm going to skip many slides. We also worked on the lithium oxygen batteries, lithium air battery or lithium oxygen batteries. Here the key issue is that oxygen evolution reactions. Oxygen evolution reactions is key reactions in the lithium air battery or photocatalyst by water split. So we figured out that here nitrogen doped graphene is quite good, or nitrogen doped graphene overlaid with copper is quite good catalyst materials. Or hexagonal perovskite with a certain amount of defect is going to be the best. Okay, we published in Jack's paper last year, 2 years ago. Yeah, we figured out that if you have certain amount of oxygen defect, then you're going to reach the best performance. Another material we developed is that for hydrogen productions. In hydrogen electric vehicle, you need hydrogen fuels to drive the car. So now there is a strong development of research work how to design the materials produce hydrogen gas. We figured out that zirconia is quite a good candidate. This picture shows that typically zirconia is white. You know the sun cream. Zirconia has white colors, but if you have small defect of oxygen, the color completely changed to black. You can see by your eyes. Yeah. Okay, we computationally figured out that you know the band gap. Yeah. White zirconia has wide band gaps, 5 electron volt. Compared to these materials, silicon has 1.2 electron volt band gap. It's a semiconductor. It's much big wide gap than semiconductor. It's definitely insulator. But if you have a certain amount of oxygen defect, you can find out band gaps at 1.5 electron volt. This is amazing. Yeah. With this band gap, this is very similar to actual silicons. Then you can utilize all visible light to water split. Then you can get hydrogen fuels. Right? So I provide you, I suggest that you can design black type zirconia by small amount of oxygen defect. Yeah, oxygen defect. Then you can find out very good properties. Yeah, recently we published in the another journals another type of HER, hydrogen evolution reaction catalyst materials by pyrite. Yeah. This is very long pyrite materials. We provide the activity of different product pyrite. The only thing is that you have to enhance hydrogen absorption at the surface. Then you can go to volcano. Yeah. you can guess what type is there, right? What material should be there. Then you can easily guess and you can publish in Nature. How about this year I published a one paper in advanced energy materials that if you design amorphous and crystalline structure, then you can have the best HER activities. Yeah, that's what I want to provide you, suggest you. We utilize the phosphorus sulfide amorphous type of capsules, and then cobalt phosphorus core crystallines. We found out there is very good activity in hydrogen evolution reactions. Yeah, this is just another type of materials, transition metal dichalcogenide for hydrogen evolution reactions. You see here, activation barrier depends on the materials. Yeah, we screened 250 different materials. What we found was that we made a database which material is best for hydrogen evolution reactions. If we figure out one niobium type materials is best. So this paper is under review in non-energy. Okay, my last topic is that can we have good robotics to study this kind of huge database? Right? What we do, we have a certain methodology under development in my lab, and one of them is neural network potentials. The neural network potential is that if particles given, you just divide particles at different regions, and you can localize the interaction potential between atoms on given regions. Then you functionalize these potentials to robot understand. Then any kind of materials you easily predict what is going to be the most stable structure. Here, for example, platinum copper, what is the most stable structure? I mean, once the machines understand the potential, then they easily predict the most stable configurations, like that. It takes 1 second, 2 seconds, something like that. It's much better than other. I mean, if you use it, typically the conventional first person calculations, it takes 1 month and 2 months. But if you do machine learning, you can get the result 1 second, 2 seconds. Huge advancement, actually. Okay, so we found out the best actually materials, platinum, copper, and nickels, for hydrogen-driven electric vehicles, catalyst material. Yeah, this is kind of strains, surface strain field on the nanoparticles. We found out that platinum on the surface, they are under compressive strains. Compressive strain is good for oxygen reduction reaction catalyst materials. Or recently, I'm also working on the polymers. Polymer. Can you predict polymer structure? Polymer is difficult than crystalline because polymer can fold. They can fold. They can change the topology by themselves. So it's much difficult than crystalline. Crystalline has very rigid framework, so we don't need to worry about folding or something. Strong entropy effect. But here there is very strong entropy effect. We discovered and we developed a methodology. We can actually describe the folding and rotations, any kind of topology change with a certain machine learning technology. Okay, I'm going to wrap up my talk by these slides. I hope I showed that the first principle computations, even though it utilizes quantum mechanical law, but still there is a huge gaps, the reaction time and material size. So we need a proper methodology to predict material property very well. So material scientists or computational theory guys, we have very good material informatics technology, which includes machine learning or neural network potentials. Then you can provide certain candidate and how to design the material for better performance. And maybe experimentalists they can design, synthesize realistic, and then they measure our prediction, and they can give us feedbacks, and it develops methodology even better. Then kind of very good collaboration is going on, right? Okay, this is my fund managers. This is my group peoples. I really appreciate my students. Without them, I cannot accomplish this kind of research work. Okay, maybe in the future, weekends, maybe you need only mouse and you can click it, any species with pair tables, then you're gonna find out all different material properties. Yeah. Then also, if you want something material to have this kind of functionalities, then you can find out how to design, how to make allies. Then you can save your time, temporal cost, and also monetary cost for the experiment. That's my hope. Thank you very much for listening. I'm going to finish my talk.